Howdy. Howdy, 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 howdy. I think it's time to drag down the volume of the Legend of Dragoon OST slowly. Let's do that. Dragging. There we go. Cool. And then to kill the tab, because otherwise we will spontaneously combust. Very good. Very good indeed. Let's do that. Bam. We're back. Hello once again, computer. It has been eons. Eternities stacked upon eternities. 8 full days. That's more than the week. Too long. Too long entirely. So tonight I think we're gonna have to get into some good business. Get into some really good stuff. Some real shenanigans. Some deep magic. I think where do we even leave off? It's been I'm losing my marbles here thinking about this. It's been a minute. I think where we left off is last sesh we had together, our last session together. We grabbed information about all of the moves and all of the Pokemon species out of the Pokemon Emerald decompilation. And we used that information to, well, we did a bunch of like regular expression search and replace nonsense to format all of that data as eLisp forms of the appropriate composition. So now we have all this data, right? Like, so we have every move in the game here, all the data. We're not using all the data necessarily, and we don't have all the effect functions implemented. That was TTS. But we have all the moves. We have their number and their name and their type and power and all that jazz. And also all the species. So, and these are ordered, we have to remember, according to the game's internal numbering scheme, not like the standard Pokemon numbering scheme. So some of them are, I think number 411 is Chimecho instead of whatever. It's weird. It's weird. There's like a gap somewhere due to a bunch of unknown variants, and like there's stuff going on. But we have all the data, right? We have all the base stats and all the types and all the abilities for every single species. So we're kind of running out of things. We're running out of things we can procrastinate on, right? Because sort of the main thrust of this AI project has yet to be accomplished, right? We've gathered a bunch of data. We implemented some moves. We've built our battle simulator. We haven't actually built the tree search. Yeah, we don't have a tree, and we're not searching it. So I guess we can talk a little bit about that. I think we're going to do some thinking out loud together, and we'll see where we get. So let's talk about some details of the problem. Let's think out loud. So one of the reasons why, so in sort of a standard, like if we were applying Monte Carlo tree search to Go, for example, right? Go has two major differences compared to well, maybe only one major difference from which other differences stem, right? So the main difference is that Go is deterministic, right? In the sense that when you play a move, the resulting game state is always the same, right? Whereas here, the difference is if you use a move, right? If you select the action, use the move Flamethrower, right? There's a whole bunch of different states that the game could end up being in, right? Flamethrower there's damage variance on every move, right? So you're not always guaranteed to like even deal the same amount of damage or even KO the opponent, right? So whether or not the opponent faints could differ, right? And there are also secondary status effects, right? Such as whether or not the secondary burn effect is applied. So really, like tons and tons, there are there are non-deterministic differences in the state that can the resulting state after you take an action, and those differences are not just like necessarily like even just numeric, right? Like they're not just like quantitative differences. They can be qualitative differences, right? Like and they can affect moves that can be made in the future, right? Whether or not the opposing Pokemon is fainted affects what the opponent can do on the next turn, right? Because if they did faint, they have to use the fainted switch move, right? And the turn after that, they have to like select moves from a different Pokemon, right? There's complexity there. So we have kind of this combination of what do you say, like non-deterministic actions, as well as a changing action space based on the state, right? So which is what makes it really complex, right? Because not only do we not know what state we're going to end up in after we use a move, we need to know what state we're in order to determine what moves can be made from there, right? So we're kind of considering this open loop approach, right? We'll still do something kind of like that, right? We're considering this open loop approach where we're kind of we don't really keep track of definite states. We sort of keep track of paths along the tree, and just sort of the traces of moves that were made, and sort of instantiate those traces by like generating new new states, like by actually like applying the moves as we go, and seeing like, which of course is like non-deterministic, right? So like kind of like reifying a it's like inflating one of those you ever have those like, what are those little things, like the sponge animals that you put in water, and they little dinosaur eggs that turn into like a big dinosaur sponge thing, sort of like that, right? The trace in the tree is kind of our little dinosaur egg, and we submerge it in the waters of randomness, and it can blow up into a number of different things, a bunch of big shapes. So but that approach doesn't really work super well in the presence of a changing action space, right? Because let's say you have a sequence of moves, like you have a sequence of actions you're supposed to take: action 1, action 2, action 3, action 4, right? It's possible that after action 2, the outcome is different, such that you can't take action 3 anymore, right? So suddenly you're blocked off from like kind of reinstantiating your state from the sequence of actions. It's so that's tricky, right? That's a real puzzler. We've been puzzling over that. I certainly have been. You might be as well. Well, I guess I don't know, but I've been puzzling over that. And in my puzzling, I found a thing that's convincing me that like I'm not overlooking something super obvious. Is someone asking the same question on Stack Overflow, like the exact same thing, like the presence of state dependent action spaces in non-deterministic Monte Carlo tree search with like an open loop approach without chance nodes, and it was unanswered, and I thought that summed it up nicely. So we've thought of a couple of things, right? So one thing we can do is, one thing I've thought of is, maybe we just make it so the action space doesn't change, right? Maybe we make it so that the action space, we can kind of evaluate the action space during rollouts versus during like tree expansion, tree growth differently. By that I mean, when we're considering like the actions that actually form the branches of the tree, we can consider a fixed set of actions that consists of use one of 4 moves and switch to one of 5 other indices, right? Without considering the validity of those things. So that will always be the set of actions, right? Use one of the 4 moves. You like use move 1 through, like literally the alpha, the I don't know, the set of symbols M1, M2, M3, M4, S1, S2, S3, S4, S5, like will be the actions that are possible, one of those symbols. And then we can simply weight invalid moves as losses, right? So in not all instances can you take action S5, right? Because, for example, the Pokemon in that index could be fainted, for example, or in not all instances could you take action M2 because maybe that move's out of PP, or you only have one move, or you fainted last turn, so you have to use a switch. But and in those situations, maybe we just consider making that invalid move just like, yeah, that's instantly losing the game, right? That's you could not make that choice. And then we can always guarantee that we can reinstantiate a state given a sequence of moves. It's just that sometimes that state is going to be an immediate loss if the moves are invalid. I'm sort of worried about that, right? Because I imagine we can end up in situations where there are a whole lot of invalid moves, right? And then you just have like tons and tons of spurious losses. And it makes situations where, like, yeah, maybe just the action space is a little constrained. Like, it also makes you much worse at solving end games, I would think, right? Because like when you're down to like one Pokemon, right, you're gonna have a whole lot of invalid moves, right, due to like the switches to the other fainted Pokemon. But like that doesn't mean you've lost, right? But that's going to like I guess I don't have a good grasp on how like the statistics of that would play out. And it makes me like sort of my first intuition is that it's going to make it require a ton of rollouts in order to like I don't know, like overcome that kind of thing. Like we just need a huge samples maybe. So that's one way. Like that way would probably like definitely like is possible to implement pretty easily. It would just be kind of tricky. Another way that I guess has similar flaws is to just keep trying, right? So say we have a path in the tree, right? We have action 1, action 2, action 3, action 4, right? We try and take action 1, and then we try and take action 2, and if we can't take action 2 because the state is such that action 2 is not a valid action, we go back to the beginning and we try and take action 1 again, right? Just like repeatedly attempt to get into a state where we can take all of the actions. That is sort of tricky, right? In the sense that like it's possible, I guess, for a state to be very unlikely to arrive in. If you like, I don't know, if you wound up in a state because you made I don't know, like I guess we'll have to read a little bit more about Monte Carlo tree search and kind of figure out like exactly why we might have to tune exactly how we're adding nodes to the tree, right? Maybe we'll require a certain number of like samples like representing a node before we actually like add that. I don't know. We'll think of something, right? I can imagine a situation where we have like we have a path in the tree that represents a very unlikely state, and then we have to like, I don't know, we have to like do like some thousands or millions of simulations to end up in a state where those moves could be made in that order. That's obviously not ideal. So I don't know. We're thinking hard. Let's stare at Wikipedia again. I think Wikipedia diving, that's often it's a useful thing. Let's do that. Let's get our Wikipedia up. Let's see if we can glean any facts from this description of this algorithm. Let's see what we can glean, right? So each round of so basically what we're doing in Monte Carlo tree search is repeating 4 steps for as long as we have time to pick a move. We're starting from the root node and selecting child nodes until we reach a leaf in the tree. A leaf is basically a node where we haven't yet done any rollouts from. We have not yet run any rollouts. And the essence of how we select child nodes is kind of like the essence of the thing. That's like the UCT algorithm, right, for actually picking the child node, and kind of balancing the usual AI balance of what is it? Exploration versus exploitation or something, right? Like balancing learning new things versus utilizing what we already know. So we select a leaf. If that leaf is not a decisive end state of the game, a win, a loss, or a draw, create new child nodes representing, of course, the actions that are possible to take from that state, and pick one and complete one random rollout from that node, and then we use the result of the rollout to update information about like number like update the ratio of wins to plays, basically, from, and we'll have two such ratios, like, or at least our ratio will just represent like the win ratio for one player, and of course just the kind of the complement of that will or one minus that will be the win ratio for the other player. I don't think we're considering draws. So then we use the information from the playout, like whether or not the rollout was a win for player one or player two is used to update the kind of information on the nodes, on the path from that child node to all the way up to the root. Okay. So in our context, right? What do we do? What do we do? So if we're considering the random approach, right, where I wonder if there's an approach where we cache states. That kind of has a similar problem where where we can, like, so the thing that we want, right? Ultimately, the thing that we want is we don't want to be misguided by unrepresentative roles, right? So my fear is something like this. So like we make a move, right? We add a child node. We generate the state for that child node. If we just do that kind of like naively, right, and we only generate that state once and like cache it somewhere, we're going to end up in a position where the like if that state is sort of like far from the kind of mean state, like mean state in the sense, like, of course all these things are uniformly distributed. I guess I mean mean state in the sense that like you could imagine situations where there's a 1 in 256 chance that you use a move and the opposing Pokemon faints, and there's a 255 and 256 chance the opposing Pokemon does not faint. I don't want to randomly roll the occurrence where it does faint and then weight that move such that we're always assuming that move faints, right? That seems like the worst possible outcome, right? Because then we sort of like learned and are not correcting on like a very bad assumption, right? So how do we beat that, right? Like what representation do we have for nodes such that we can beat that? So, I mean, one thing we could do is just like run a couple of samples, right? So we could do it like so something we could do maybe is it's tough, right? Because I also don't want to like have to think very hard about that. Like, I mean, of course, we could make a much more complex state representation where we're caring a lot about like kind of like everything is stochastic, right? Like, and like that seems very tricky, right? Like we want the state to be like this fully concrete thing, and we don't want This is a real puzzler. We gotta think of a good way to do this. And I'm not a statistician. I don't know anything about any of this shit, right? I know the law of large numbers, and that's about it. That's a rhyme. It's going Dr. Seuss mode up in here, my man. But yeah, well, let's keep thinking out loud. We're gonna power through this, because we're gonna think of something, and whether or not that thing is good, we're gonna implement it, and then we'll see if it's good. So maybe a thing is like, okay. I really like the idea of just representing paths of moves and instantiating those paths, right? I think that is that's a winner, right? And the tricky bit about that is that we can't always follow a path, because the intermediate steps in that path, we're not like we're skipping along a river, right, from stone to stone, and sometimes we will slip and fall, right, and we're not going to get to the next stone. So what can we do about that? We can cache the good states, right, and just use that path. But then we're stuck in, we can get stuck in weird spots and confuse ourselves, right? We can get confused by outliers, basically. We could cache a bunch of we can try a bunch of things, right? Like we could cache, I don't know, like when we're selecting the child moves, right? Yeah, I guess that's the thing we can do, right? So when we're moving, let's see if we can move the mouse around, right? When we're moving from like here to here, right? This could actually be a, oh, it doesn't work, right? Because then either we have, so what I was thinking is like, maybe this is a selection of a set of 5 states, right? And this is a set of 5 states, and this is a set of 5 states. But the problem is, if you're moving from here to here, you have to pick a state to apply the action to. So you're still picking a state. Well, I guess one way to remove outliers would be to like run the action from the here to here, right, or any other path, any other edge, right? Run that edge like 5 or 10 times. Pull the set of actions from take this, get the set of actions from each resulting state, and you can't just check the intersection, right? Because there's not always going to be an intersection, right? But you kind of want like the, damn, I wish I remembered more terminology, right? You want like the largest, like the thing that is closer to the intersection, right? Like you want the action that is in the greatest number of those sets, right? So if you like run the action represented by this edge 10 times, right, you're going to get 10 new states, right? And from each of those states, you can get a set of possible actions that can be taken. And so now you have 10 sets of actions, and they're not guaranteed to intersect at all, right? But of those actions, of those 10 sets of actions, you can I guess, yeah, find the action that occurs in the most sets. And then, well, you want a set of possible actions. Oh, okay. So what you do is you find the action that occurs in the most sets. And then you find the largest set that contains that action. And then you kind of use the state that's associated with that to pick your next actions, right? So you're kind of guaranteed to... Well, no, the whole point of this is that you're kind of exploring all possible choices, right? That kind of naturally weights... Like, it weights the tree search towards choices that lead to, like, more predictable outcomes, I guess. I don't know. This is getting off in the weeds a little bit. A little too much for me, I think. It's tricky business. Right? Does that make sense? Does that make any sense at all? Like, it feels arbitrary, right? I don't like that. Well, let's think. Let's think. We'll think together. Put on our thinking caps. We'll have a little think. What else could we do? What are other approaches? We have to strike the right balance between... So one thing we do is we could represent actions as sort of a pair, right? We can multiply a little bit. We have a little Cartesian product action going on. We could multiply our space of actions and have actions be the action and then the resulting state. That really embiggens things. I guess that's probably roughly the same as adding chance nodes to the tree, and also a lot easier. So maybe we'll keep that one in our back pocket. But the thing is, like, again, that multiplies the space of possible actions, and therefore multiplies the base of the exponential that is the size of this tree. That seems not ideal. But maybe that's what's warranted. I guess anything other than that is, like, I don't know, necessarily kind of this heuristic thing. So I don't know. Complicated stuff. Jeez Louise. Really complicated. Let's... As much as I want to not think about this, we're gonna keep doing it, because I think tonight is the night. Tonight is our grand adventure into actually convincing the computer to play a game for us instead of just setting up the stage props. I think it's getting close to time. Okay. So what if Well, so what are the approaches ranked by difficulty, right? I think the easiest approach is going to be request a random reroll when we can't take an action. Probably okay, so what is probably the most principled approach is... So we're talking about this UCT algorithm, right? This thing that balances exploration and exploitation, right? This is what we basically compute this for each node, and we that's how we pick the node, right? Whatever node has this expression at the highest value. The kind of thing that feels principled to me is to incorporate our how do you say, certainty in the outcome of a move that's represented by the actions that are possible to take following that move. We incorporate that certainty into this weighting somehow. But the problem is like that still doesn't make sense, right? Because like, so say let's consider our flamethrower situation again. One person uses flamethrower, and then from the next move, right, there are going to be like normal actions acting as if the flamethrower did not feint the opposing Pokemon, right? The opposing Pokemon using moves. And there's also going to be an edge from that node corresponding to the feinted switch, right? The forced switch in based on the feint. So it's not like we can attach this sort of confidence information to the node, right? It's something that's attached to the edge, or to an edge that's coming out of the next node. And that's tricky. Well, I guess it's sort of like, well, we sort of need rollouts. Oh, well, maybe that's interesting. That's an interesting thought, actually, right? So in the same way that these rollouts convince us, right? Running random rollouts convince us of give us more confidence in the quality of a move, right? Doing random instantiations of the tree might give us more confidence in the I don't know, that a given move is not so much of an outlier, right? Like the kind of the feasibility or our confidence in our ability to take a future move, right? Because that's really what we're expressing, right? We want to have an appropriate level of if a certain plan of attack is dependent on a 1% roll, we want to incorporate an appropriate level of confidence that, like, with respect to that 1% roll, right? We want that to weight our EV, right? If we end up in situations where it's like, oh, we can win if we make this move, but we need that move to land a 1% crit, right? Or like roll a high damage on a 1% and kill. We want our expected value of taking that move to be appropriately weighted. So how do we incorporate that? Well, I think a natural way to incorporate that is, honestly, I would feel better if the AI plays more conservatively, right? Like, realistically, right? If the difference between move outcomes was only numerical, like, I would be just using the average, right? I would just always assume moves do the average damage, but of course that doesn't work, right? Because like, you can be KO'd by a move on a 1%, right? And some or on a, right? You see, and like, you have to incorporate that. You have to plan for that potentially happening. But you want it to be incorporated at an appropriate weight, let's say. So maybe we can kind of have two levels of this sort of, I don't know, simulation and backpropagation, right? We can have the level of the kind of the world level of simulation and backpropagation, like actually running rollouts, simulations of the game, which gives us confidence about the chance to win. And we also have the kind of the rollout mechanism of instantiating a part, like a tree, right? Instantiating a state from a sequence of moves. The success or failure of that instantiation gives us confidence in one or more of like where we fail in that chain, where we fail to go from one state to the next state, gives us information about the how confident we should be in the preceding moves, I guess. But either way, what this is telling me is I think there's room to explore here in the kind of the easy approach, right? Where we're just randomly randomly like repeatedly trying the instantiation until we get a good result. So what okay, let's make a plan of attack. What we're going to do is we're going to implement a representation of the tree, of the game tree. The nodes of the tree are going to be lists of actions. The edges of the tree are single actions, which are sort of implicit, right, in the transition. We don't really need to represent the edges, right? It's just like the child nodes will have a new action const onto the list or something, right? Like it's easy. And we will write a function that can take a node in the tree and turn it into a state, right? Easy enough, right? You just take the root state and randomly and just apply those actions repeatedly. If you can't apply them, then you give up and we apply some strategy to do something else, right? Either we throw it away, or like we can do some kind of tree search waiting thing, or update some weights somewhere, try again randomly, all kinds of things. So I think this is what we will do. Let's get started. Let's dig in. What's in this file these days? I wanted to kind of move this stuff into a file specific for this simulator. Where's simulator.yl? Because this is like simulator stuff, right? It's telling us how to resolve a move, how to simulate a turn, right? This is related to just it's not specific to the tree search, right? Whereas here, let's go here, let's go here, let's grab this, sure. Grab that, do standard string stuff, fine. In here, we're going to have the actual kind of machinery for the AI. So let's include everything we need. We'll grab some libraries as well. And let's put rollout in here as well. That seems like, because rollout is more of an actual AI thing, right? That's battle simulator. We're gonna say Monte Carlo tree search. We're gonna get completion for every Pokemon name now, because we have I think, right? When we're writing comments, at least, right? That's very funny, because we have all of those names as strings in another file now, so it's using this kind of string completion from other buffers. All right, so we have our rollout machinery. What other machinery do we have? Let's say we have this AI types file. This is mostly things for the simulator, right? Yeah, but what do we call type definitions? Sure, not really type definitions, but that's fine. I'm mumbling at this point. Let's keep our energy up. Let's see. We have tree node. We're going to call it tree node because node just seems a little too generic. Make tree node. What does a tree node have? A tree node has a tree node really just has children, right? It doesn't even need like the specific path to the node, because that path is sort of implicit in the path from the root down to this node. Well, it's also going to need like confidence values for the backpropagation, but that's yeah, I guess we'll add that as well. And really is naming things is the hardest part, right? Because the way you name things can just totally shape the way you think about things in the future, right? Calling something like, I don't even know, like node versus vertex, right? That it can totally shape the way you consider the problem, even at least for me, right? It'll kind of bring to mind different associations, right? And it can really make a difference. I think it's important to give things the right name, so it's worth thinking about. All right, so what does this have? It has children. Children is just nil. What is children going to be? Why are we frozen? Did I press caps lock? What's going on? Did press caps lock. There. We've uncaps locked ourselves. Gosh. I need to make changes. I'll probably end up disabling caps lock in the X mod map or whatever. Well, that's something for another time. I think this is a mapping from action to tree node, where action is one of these actions, right? Which is, it's just basically a symbol and a number, right? We can eke on these. Like there's reasonable notions of equality here, so we can have like an A list or something like this, or a hash table if we really want to. Cool. So that's a tree node. Well, we also need information for the propagation, right? So we need team 1 wins. Zero. Rollouts 0. So yeah, we'll just keep track of how many times team 1 gets a win, how many total rollouts we do. Cool. Cool. Okay. So we have a function. We need a function to practice. We've been using this word instantiate. I like that word a lot. Instantiate node, right? What that's going to take is the root state. We'll call it the root state. It's going to take the path. We're going to call that actions. And it's going to produce a new state. Okay. Well, this is where we get back to needing to deep copy states. So maybe it's finally time to write a copy. Oh dear. Oh dear, oh dear. Sleepy here. We're snoozing. Ready for a snooze. Snoozing for a bruising. Okay. Because we need to copy states, because all of our stuff so far is because like we don't have easy ways to non-destructively update these big nested data structures. So we've been destructively updating them because that's easy. And we're going to fake non-destructive updates with copies. We need a way to deep copy things. I think the way we'll do that is Huh. We're gonna have to do some weird stuff related to the actual representation of structs if this is going to be not horrible. I think you can copy structs with copy sequence, which implies that structs are sequences. So all we really need to do is map over them and recursively copy each. Well, maybe it just looks like this. Smarag copy struct S. Does it look like if sequence P S copy struct well, something like this. Otherwise S. Is this the right thing? Right, so if the thing is a sequence, recursively call this function on it. Deep copy the structure S. If the thing is a sequence, recursively map over all the elements of the sequence and try and do this thing to them. If it's not a sequence, just return the thing. That right? I wonder if it's right. Okay, we're going to assume it's right. At least it has the right interface. And if it's not right, we will we'll fix it up later. We'll deal with the consequences of our actions in the future. Future L Colonq is our worst enemy constantly. We're trying to put them under as much duress as possible at any given time. So I think this will be a good step on that journey. All right. What is up next? Next. Let's see. Well, we're doing this instantiate node thing. So what we want to do is we want to say, well, first of all, st is copy struct root_st. That's a given. How the fuck do you do this in a language like this? This is usually just, I mean, all we have to do is recursively grab the first element of the list. It's a conv list. That should be like bread and butter, but I don't feel like that's the idiomatic way to do that here. Maybe it is. I mean, also, I guess we just do this, right? Like that's realistically the way. What we say? Okay. Create a new state by applying actions to this. And actions here. This is actually okay. So things are actually more complicated than we think, right? We've been ignoring one very crucial element of this whole shebang, which is that we only control 1/2 of the actions, right? There are other actions that can be taken. Well, I guess it doesn't matter, right? There's just a bigger action space than we thought, right? It's just we can't always pick the action, but we get to pick 1/2 of the action, and we get in that case we'll end up just averaging the. We could model the opponent's actions as well, right? Like we can assume that the opponent will do the thing that will we'll so if both players can take 4 actions, right? We'll be modeling the 16 possible actions, like pairs, and we'll know, we'll have estimates from the Monte Carlo tree search of like both players' win rates from all of those 16. So we'll just assume that the opponent will take the best move, which is I guess that's a heuristic, but like we'll assume the opponent will take the best move out of their actions, right? They will take the move such that they are most successful regardless of the action that we take, and then we'll model ourselves after that. I don't know. Like again, that's very heuristic, right? That's like there's layers upon layers there. That ends up in like rock paper scissors metagame territory where it's like kind of impossible. But okay, for each action, we're gonna assume these are pairs of actions. What are we saying? Simulator, do we have a simulate turn? Yeah, we do. Simulate turn. ST. Hey, it's getting mutated. We don't have to track the return value or anything. How convenient. Car it. Cutter it. How easy. So that lets us instantiate turns by applying actions. We should make sure that simulate turn returns, like we need a little more here, right? Because we need to check if the actions are valid. Right? So here we say actions 1, right, this battle team 1, ST, right, this team valid action, yeah, team valid actions, that sort of thing. And same for 2. Okay. And, well, how do we do default? We gotta Google. We gotta Google. Back to Google. eLisp default. Well, we'll be braver, right? We're just gonna check CLDefun. Oh, we can just do optional. Does normal? Not going to tell us what the arg list is. Well, if we just say optional, I don't know, fuel 10, right? This is the number of times we're going to try to instantiate the node, right? So here we say if contains actions 1 car it, and so if the list of valid actions in the current state for team 1 contains team 1's proposed action in this sequence, and similarly for team 2, then we actually simulate the turn. Otherwise, we try the whole thing again from the beginning. You might ask, why is this? Yeah, that's why. Oh, that's why. We do need to CLDefun. Sure. You might ask, why do we start from the beginning? Why don't we continue from ST? ST's gotten part of the way there, right? If we have a sequence of moves that's 10 moves long, why aren't we just why aren't we reusing all the work we already, why are we starting from scratch? What is this? The reason is we can get trapped, right? And it might turn out to be better to do that, actually, right? We'll have to weigh that. But like, I mean, you can imagine a situation where like a bad roll in turn 1, I mean, you could still take the action you want on turn 2, and on turn 3, that action is not going to be relevant, right? So if you just keep simulating from turn 2, you're never going to get a state where you have the action you want. So it is kind of safer just to start over from scratch. But we're only going to do that up to fuel times, right? We're going to say when greater than or equal to fuel 0, do any of this. No, don't indent that far. Like so. Otherwise, return nil. That'll give us some flexibility, maybe. So we'll try. We'll try up to 10 times in order to get to a path that we've picked, but we won't try very hard. And this is where, if we decide to do our kind of double backpropagation scheme, we would add, like, every time we're trying, we should make it less likely that we want to simulate from this node in the future. Maybe even now, right? Maybe even failing to instantiate the node here makes us consider another node within this same round of Monte Carlo tree search. That would be exciting. I need need more props for my model. We're gonna have to do that soon. We need another guidance stream. I'm feeling that. We need some lab sessions to build some extremely fancy streamer tech, techno toys. I'm feeling that. It's feeling good to me. But I digress. So here, okay, we have a tree. We can instantiate paths in the tree into states. What does the tree search actually look like? Well, we need to, if I do that, does that work? Yeah, it does work. Holy moly. Space age stuff here. Well, I guess we just implement this, right? So I think we're going to want to structure it as, instead of a function that just like loops and does these rounds, we're going to want to be able to run one round at a time, right? Because we don't want it to block, right? We want some asynchronicity happening. We probably want to visualize the tree at some point. So we'll make something that does one round. Let's say, okay, keep on largest round. Okay. And we have a root state, as you do. We have what else do we have? What else? Root state, right? So from here on out, right, I'm trying to think if we need where we need to insert copies for the root state. I think kind of the invariant we want is that none of these functions should ever actually modify the root state, right? And these are kind of like the high level things that we are using, right? We're gonna call this root state too, just to be consistent. And we're gonna say things like, no, st is up destruct root state. Just so, like, yeah, when we start a rollout, we're gonna clone the state, simulate from there. That seems like the right thing. All right. Yeah. Okay, so we have Monte Carlo, we have one round, right? we start from root state, right? And what is this going to return? This is going to return, and we also have a tree. And we're going to call this root node. And what we're going to, this is going to mutate the tree. This is going to update the tree. The information done, with information we learn from doing one round of selection, expansion, simulation, backpropagation. So what we need to do is we need to pick a leaf, evaluate the leaf, pick a child from the leaf. Where a leaf here is just any node that has a potential child with no rollout. Is there a cleaner way to represent that? Right? Do we just always add? When we would add all one child, we always add all children, and we consider leaves just nodes that have no playouts completed from them. I think that works better. That's kind of a cleaner way to think about it. Maybe? And if not, we'll learn why it's not soon. Or not. We'll see. Wait and see. Okay. So we pick a leaf. There's this expansion step that we're gonna have to. I guess maybe that's why we're learning why it's not so easy. Well, maybe we do that. Well, we're gonna have to see. Basically, we just do these 4 steps over and over, and we have the simulation step, right? We can run a rollout and get a result, right? We can even run a rollout with limited fuel and get an unknown result, right? Sure, that's fine. And in those cases, we're probably gonna want to do shit like have a heuristic, right? I can imagine a situation where we want our rollouts to only go like, I don't know, 25 moves in the future. And if that doesn't lead to decisive victory, we have a simple heuristic like, I don't know, number of Pokemon, compare a number of fainted Pokemon on both teams. That seems easy. What else can we do? Then we backpropagate, which I think is also relatively easy. That's just we move up the tree. We'll just keep track of we'll accumulate like a list of references to the nodes to get to like the current node that we're on, and then just do that instead of like having parent pointers or anything like that, because that's awkward to represent in this language. Awkward. Yeah. Yeah. I'm feeling it. Real. Welcome, Satan, my ninjas. It's a nifty name. Thank you for the follow as well. Hope you're having a grand old time of it. We are digging into some Wikipedia presently. We're trying to figure out exactly how we are going to finish up our Monte Carlo tree search implementation that plays 3rd generation Pokemon battles inside of Emacs. So perhaps we will be successful, perhaps not, but it'll all be here on in color video at glorious 10 FPS. Let's keep thinking then. So, what do we do here? We want what language you read. So this is Emacs Lisp. It is a Lisp that is commonly used as an extension language for the editor Emacs. And we're doing it because it's a lot of fun. It is certainly not the best choice to write some performant AI, but it's a fun choice, and it's going to lead to potentially fun things in the future. So we'll see. Makes it easy to do things like visualization, I guess. But it has certainly good editor integration. But who knows? So what are we doing? Pop back over here. So first we need to pick a leaf, right? And well, in this case, a leaf is any node that is missing any of its possible children. Could we equivalently state that as any node? Well, we sort of have like multiple states for nodes, right? There's kind of like the initially added. There's a node can be not in the tree at all. It can sort of be partially in the tree, in the sense that a rollout has been run from it, but its children have also not been added to the node. And it can be in the tree and its children have been added. So maybe we're going to put off the selection step for now, because the selection step is also the part where we have to implement UCT, right? So let's implement the other steps. Let's see. Let's say expand tree, right? We still have a root state, because we're going to have to instantiate in order to expand. Or maybe we have to do all of this in order to, like, I'm trying to think like what architecture gives us like the most sharing, and is going to be the least like clumsy moving forward. Not super sure. Language is so awkward. I miss Haskell. What shall we do? We're always doing playouts from new children, right? I mean, that's something to consider, right? Like a rollout is never going to start from the same node. Does that influence our choice of representation? I wonder. What to do? Well, does that also mean? Okay, we need to add some. Let's see. We kind of need to keep track of the available children of the node as well. Maybe we just. It's frustrating because that it sort of requires us to instantiate earlier than we would like, right? You kind of have to, in order to pick a leaf node, right? In the sense of where a leaf node is a node where at least one child has not had a rollout completed. Like, we need to know what the children of the node, what the children of each node are, right? Like that's it's tricky. So we need a different representation of. We need a different definition of what a leaf node is that will still be workable. right? Like, can we just consider actual leaves in the tree, right? And that is the end of paths as and then so we pick an actual leaf in the tree. We instantiate the path to that leaf. We add all of the children. We pick one of them and run a rollout from there. Like we pick one of them using UCT or whatever, or the open loop UCT or whatever. Some heuristic that does the right balance for us that we'll probably have to tweak and go from there. Like the issue there is that we'll only ever pick one child of each, right? We're never gonna get like, there's no like horizontal, there's only vertical movement in the tree. There's no horizontal movement. That's kind of tricky. Oh, here's a heuristic, right? Or not a heuristic. Here's a strategy. We pick maybe not. Let's, because like what is the oh, I think I see, right? We pick a leaf. If at least one rollout has been run from that leaf, we add the children and run a rollout from one of the children. Otherwise, we run a rollout from the leaf itself, right? This ensures that we don't kind of like consistently skip with siblings, right? Like we're always going to pick a leaf and then, but it makes the initial leaf selection process. No, it doesn't. It's fine. It'll be okay. It just sort of delays that. Maybe it makes us run some extraneous rollouts, but that's probably fine. So what do we want to say? Expand tree. Actions. Actions is going to be the so the way this function works, root state is the state, right? The actual state. Actions is the path of actions that was taken to get to the leaf. Leaf is the actual leaf node that will mutate. So where to go? How does this work? Given root state and actions, path, add, return the possibly expand the tree. Return the base, the state, starting state for the next rollout, right? So what this is going to do is we're going to check if leaf, okay, if the rollouts count on leaf is greater than 0, add all of leaf's children, like instantiate. So what this is going to do, we're going to instantiate the path of actions from root state to get a state that corresponds with leaf, right? That could fail potentially if given randomness, which we'll handle at some point. We get a state that corresponds with leaf. We'll only do that if, I guess we need to do that both ways. Yeah, so we'll get a state that corresponds with leaf. if the leaf node has 0 rollouts, just do nothing and return that leaf, that state that's kind of corresponding to the leaf node. If it does have rollouts, compute the valid actions from that state, add them all to the tree as children of leaf, select one of them according to UCT, perform that action on the state, right? Get a state corresponding to the child, and then return that state and node probably. State, node, and state for the next rollout. I think that's good. Yeah, that seems like the right thing. Kind of have a clunky representation here, but like I think it's fine. We're sort of keeping things straight. So first we need to instantiate the state, right? So let state equal to instantiate node, root state, actions. Okay. We'll say, okay, if equals practice tree node, we gotta reevaluate this. Tree node rollouts, leaf 0. Then we just return a list of leaf. Well, we're gonna do this in the same order that we passed expand tree, right? State path node, right? So the state is now st. The path is actions. Well, no, reversing is better. Path node state. That's right. That's the right thing. Sort of, it's not a state that corresponds with root state. It's sort of another thing, right? It's instantiated state. That makes sense to me at least. Path will be action still because we haven't taken another action. This is just the instantiated state from this path. Still the leaf node. We're starting at the leaf node and st. Right. Otherwise. What's up then? So otherwise, we need to say, okay, actions is Smaragdus. We're gonna do both actions 1. Team valid actions of Smaragdus battle team 1 st, and similarly for team 2. Did we do that right before when we were doing instantiate node? We didn't. That would have tripped us up, but we remembered. Very good. So we have actions 1 and actions 2, and now we want the kind of Cartesian product of actions 1 and actions 2. I wonder if we can get that, if there's an easy library function for that. That would be very handy. That's gonna multiply. Is there a pairs? Well, it doesn't really matter. It's just something like, say, action pairs is map Well, we'll do it with actual lambdas. A1 map lambda A2 cons A1 A2. This is against actions 2. Close the lambda, actions 1. I guess that's all pairs of actions. Okay, what then? This needs to be, of course, let star. So then we need to add children for all of these. I guess we just make the children here too. Children are... Did we decide that children is an A-list? Yeah, probably, right? So we just make the default, we just make a bunch of default tree nodes, right? Because they'll have a nil list of children and 0 wins and 0 rollouts. So we can, that's actually very convenient. That we just say map action pairs. That would just be cons it Smaragdus make tree node. Is that the right thing? I think so. There we go. Yeah. And then we update the children. We also only want to do any of this if the node is actually a leaf. So we want to say unless tree node children leaf. Sure, leaf is a leaf. Sure. Sure. Okay. In that case, we setf tree node children leaf to children. We select one of them. We're gonna just, what do we say? I'm gonna say nil here. Select and return child actions leaf state. Which be CT. What are you complaining about? Oh, we need ST here. ST here. What is this? Green leaf. From leaf. Excellent. Okay. So we're starting to get a picture. We need one function that selects leaves, right? Which will be actual just leaves in the tree, right? We just well, I think we do UCT there. Maybe we don't. Maybe do we do UCT also in the expansion stuff when we're choosing the child? Maybe both, right? Maybe UCT we just use to pick a child. Right? Well, we know equal the amount. Like, we should just pick a child at random when we're adding all the children at once, right? Because we know nothing about all of them, right? So that's fine, right? We don't need to do this. We've overstepped ourselves. We just pick a random one. We don't have a way to. Where's our rollout function? Oh, please stop. Rollout. How are we picking random moves? Are we just like rolling random up through the length? Yeah, that's what we're doing. So random action is nth random length action pairs. Action pairs. Sure. And the actual child node is, of course, let's get. Do we have? Are we socking a bunch? Or are we list getting? Or we're doing it with s equals here. Well, what does list get used by default? It is eq. Well, we probably want to use this equal. Is that the right thing? Yeah, we want to actually like compare. We don't just want to do like, I think eq just compares pointers, right? That's the heuristic for me to use mentally, right? Eq compares pointers, equal is a structural equality. Okay, list get random action children nil equal. Then we just return. What do we return? We return list of we can append sequences. I hope these sequences aren't cons lists, but they probably will be. Actions list of random action, and right, that makes sense. Child node, and then finally we need to actually simulate one. We need to simulate the new action, right? So we need to say child state is simulate turn st, the previously instantiated state, car random action cutter random action. We already know the action is valid because we just got them from the valid actions. Perfect. And then this is child st. Excellent. So this should, ideally the thing that this does is take a leaf in the tree, checks if rollouts have been performed from the tree. If they haven't, well, great. Just return, instantiate the state, instantiate the path to the leaf, return that state and leaf itself and the path, right? Whatever. Otherwise, compute all of the valid children of the instantiated state. Pick one of them randomly. Add all the children. Pick one of them randomly. Like perform the action corresponding with that child on the instantiated state. So we have a state corresponding with that child. and return that alongside like an updated path and an updated and the child node. So what this is going to give us is the return value of this is like kind of the starting point for our rollout. Perfect. Perfect, perfect. So this is going to look something like take leaf. Just expand tree root st take leaf and leaf actions leaf. I just roll out. Is there a good way to do pattern matching in Lisp? This is getting frustrating. Case. Case macro. This looks fancy. Very fancy. It's like just what we want. Maybe. Maybe. All these things are, I don't know, so ad hoc, right? Like these macro constructions. Frustrating. But regardless, I'm just going to call it, let's say this, right? This is fine. It's all fine. Expand res. Res is nil for now, right? And this is going to be, I don't know, let's say this is car cutter. Right, so we pick a path, we pick the leaf itself. What else? What else? Expand res is a bunch of stuff. It's a path. And then I'm going to swap these so that we're a little more consistent. It's a path, and then a leaf, and then a state. So what do we do from there? Then we say rollout res is rollout catter. Can we just say like third item, please? Yeah, it seems a lot better. I would rather say that. Okay. We roll out just from that state. That's just going to give us a symbol back that tells us who wins. And then from the rollout res, we backpropagate. Right? We loop over actions. We use the actions to successively descend the tree. Yes, along the path that we took to get to the node. And for each item we add +1 we increment the rollouts field for each node, and we conditionally increment the team 1 wins field based on whether or not team 1 won the game. Cool. Cool. That seems like the right thing. Okay, let's just make a this will be easy, I think, right? We say cl incf just tree node rollouts node. Sure. We also say well, team 1 win, right? When it's a win, let's say 1. Do the same thing for team 1 wins. We could avoid a conditional. It doesn't, whatever. The branch predictor has bigger problems than our when here. Notably the probably 100 hash table lookups that occur evaluating this. Like, really is not going to matter too much. I'd rather it be clear. Update win rollout counts. Code along path actions. If one is true, win counts are also updated. Okay, so this just does it for the root node, right? After we do this, we're also going to do it for the specific child that corresponds to actions. So we're back propagating again. The node is going to be the one that is equal to the head of actions, right? Of the children. Right, so we get the child that corresponds to the first entry in our actions path, right? Our new actions path is the rest of the actions path, and if team 1 still won. If team 1 won, they still won. Cool, nice tail recursion. Wow. How cool. We have no guarantees about that here in this fresh hell, I think. We let's hope these things don't get too big. Fine. Sure, let us continue. So we get all that stuff, and then we can just say let's backpropagate. So we're backpropagating on starting at root node. The path of actions needs to be the full path, which is what is that, second item? Yeah, or first item. First item of expand res. And this is equal rollout res team 1, right, which indicates that team 1 was the winner. Called with one argument requires 2. Requires the initial fuel. Well, we should make that take a default, like we do. Optional 30, sure. Run 1 round of on move state and root node. Very descriptive doc strings we have here. Very handy, convenient. Telling us a whole lot about the purpose of this thing. Yeah, so now we just need our selection code. I mean, of course, a lot of this is going to break. We don't have any nil checks anywhere, right? Like, and all these things can fail. But that's what we get for doing it this way in this language, and we'll add checks as we go. Because we haven't really decided on our strategy for handling errors, right? Do we just retry things? Do we what do we do? I think there's a lot of options. We could do any number of things, all sorts of jazz we could get up to. So we will see. Yes, we will see. Let's add selection. Let's move rollout also, so these things are in order, right? In the order that we're doing them. So selection, expansion, and then rollout, and then back propagation. Okay, so this is going to be Smaragdus select leaf. It's going to return the path to that leaf, and then also the leaf node itself, right? Of course, we can always get the leaf, given the root node and the path, we can always get the leaf node itself. We're just doing this, I think, to, my brain is telling me to do this to save, like, time, right? Because getting, you know, actually getting the leaf is sort of expensive, right? Like, you have to, like, do, like, iterate over the whole list of actions and do that many A-list lookups, and, like, that's maybe, you know, it's maybe a little nicer. Maybe. That's, should be doing that a lot otherwise. Okay. Maybe we do just want to attach the paths to the nodes, but like, yay. I don't know. I don't know why when I press like F2 it tries to launch the Rust language server. That's, I think it's actually jumping to a buffer that's like showing an error message from like when I opened a Rust file and it couldn't launch the language server. So that's maybe I believe that. Okay, here's where we need UCT to compute the thing. So what we do here is, I think, well, we use UCT at every point. We're just descending the tree by picking a child until we reach a leaf, right? Until we reach a point where children equals nil, and the child we pick is just determined by UCT. So how do we compute that? Expression, okay. WI is number of wins, so that's our team 1 wins. We're going to assume that we're always team 1 for clarity, right? We can always set it up so that we are. N1 is number of rollouts, sure. N, capital N1 is the total number of simulations after the ith move run by the parent node of the one considered. So this is N1 is just like the actual child, right? So this will be the child we're considering rollout count. This will be the rollout count of the the parent node, the current node in the recursive thing. C is exploration parameter. Square root of 2 theoretically, sure. We'll define that as a constant. Sure. Not too bad. So let's actually define Smaragdus child node weight, child parent, that is equal to the sum of divided by, how do we convert to a float again? Did we determine that this is how you do it? Yeah. Float tree node. Well, we're using these multiple times, right? Maybe we just grab all of these, right? We just say let w is equal to team 1 wins of child n rollouts of child. I don't want to use capital variable names. It's probably fine locally. If Emacs yells at us, we'll change it, but that's okay. This is sum of map it 3 node children parent. Wow, our indentation actually lined up. That's so nifty. Yeah, so we just map over the parents, the children of the parent, compute the rollouts for each one, and sum them. Okay. Well, we can make this, put the float, I swear. Do it like that. And this is, what is this? W over n plus, then what is C? What is C? C is square root 2.0 times C of square root of divided by, or can we just do log 2.02? Is there a constant for Euler's? Euler's natural log. We'll just copy the thing if we. Oh, if you don't specify base, the base C is used. I don't mind that. That works for me. Log of big N over small n. Let's that like that. Or yeah, we need to indent a little bit. Yeah. Okay. Oh, and this is going to recompute parent total rollouts. We don't want to recompute that a bunch of times for each child. Let total rollouts equal to this thing for the root node. I'm just going to say this is... we don't even need this to select a leaf. We just need a node. Sure. We can get the total rollouts. Compute the UCT weight for a child with parent total rollouts. They're writing absolutely horrid docstring comments throughout, but like, how much can you really write about these things? It's sort of obvious what they do. Well, maybe not. I guess that one's kind of decent, right? Like the telling us it's doing the UCT thing gives you something to Google if we get totally lost. So that's fine. But here we just and say max by. We'll just comparator. Is that random function that calls oh, so we want to do something like max by on like so. Like so. Tree node children node. We want to see, okay, if not just tree node children of node, right? i.e. if this is a leaf, right? You return node. So I want to return the path. Optional current path, right? It's fine if it's nil. Actions. We'll call it actions. That's fine if it's actions. In that case, we return cons actions node. We found it. Hooray. Otherwise, well, this is an A list, right? It's just a list of pairs. P. We want that of cutter P. This will give us the node, right? This will give us the child node with the maximum value. In that case, we just select leaf on that again. We'll be a little more clever. Let's. It also doesn't. You have to pass in total rollouts, so that's fine. Best child is like so. Child node weight needs to take the parent thing. It takes total rollouts as well, right? So here's the best child node. What's the best? It's going to be. This is the best pair of action child. Action child. Right. And then what we actually return is cons append actions list car best action child, right? Because that's the action part. Cutter best action child. Hooray. I don't know why I'm saying hooray. I have no confidence that this works, right? We haven't ran a single line of code, right? But I don't know. It's we'll have our fun while it lasts. Select a leaf node starting from node and path actions according to UCT. Did I close the buffer? I'm pressing all kinds of keys tonight. We're flailing all over the keyboard. Okay, there's our select leaf. I just select leaf. And we need to give it the root node. No list of actions, because they should be null. And that's all she wrote. So, can we actually do this now? Let's think of like how the game will proceed, how this will proceed. So we start with an empty tree and just a root state, just some arbitrary state of the game. Right? Because we're doing this every turn. The root node of the tree naturally has 0 rollouts run from it. So, and it is a leaf, right? So we'll start and we'll run a rollout from the root, back propagate to the root at, say that we suddenly have a rollout now, get a new tree. We should call this something a little different. We should say from, say, on root node. We're not modifying root state. It's not acting on root state. It is acting on root node. And then, okay, then again, we'll select a node, right? We'll select the root state again because it's a leaf. We'll go to expand. The root state will be identified as there is at least one rollout there. So we will add a child, or add all the children of the root state and pick one randomly. Then we'll run a rollout from that child, and we will well, we do need to modify our UCT maybe, because again, we have this thing where there's like multiple actions. We don't have total control over the action space, right? Because the opponent is choosing one half of the action. But we'll think about that. We'll think more about that. Maybe it doesn't even matter. Like, I don't know. Because we need to, or it will matter, right? Because we want UCT to prioritize like the opponent making their best move while we also make our best move. So maybe we need to track slightly more information, right? Or incorporate that somehow. Probably the easiest thing is just to do UCT on them separately, right? Because every child node has there's sort of a team 1 component and a team 2 component of the action, right? So we keep track of both. We keep track of, well, we know wins for team 2 is just like 1 minus wins for team, or like rollouts minus wins for team 1. So, or maybe not in the presence of peel and delay. I don't know. It would be easy to do. Maybe that is a thing that we'll do. But it'll be easy enough. We thought of it easily enough that when it comes up, we'll think of it again. So I don't think that's a problem. Okay. Well, maybe it's time to start like looking at this. So maybe we say something like test tree is Smaragdus or defar, sure. Can we just do this? Just do the thing. Set make tree node. Yep. That'll ease some of our woes of like def-var not reevaluating if we reevaluate the whole buffer. Sure. What if we say we don't want to like run a roll? We don't want to like hang up our whole Emacs yet because we don't want to like start running rollouts or anything. I guess it doesn't matter because there's fuel kind of everything, but we want to make sure that we're not gonna like loading up. If we say Smaragdus select leaf test tree, how does that work? It returns us nil actions. That makes sense. And the root node. Makes sense. What if we do Smaragdus expand tree, st, whatever our state is, nil, because there's no actions, and test tree. Okay, it doesn't expand anything, and it returns the list that we expect of the list of actions. Why are we returning 3 things and we're only using 2? What are we not needing? We return actions, the child node, and child state. Oh, we don't really need the child node, right? Because like we're just gonna roll out from the child state and then backpropagate through the list of actions. So, but it's fine. It doesn't cost much. The child node. So, nil list of actions. Why is the child state nil? Oh, because we're failing to instantiate. Why are we failing to instantiate? If we say Smaragdus instantiate node st nil, why is that giving us nil? Is copy struct? Oh, well now here's the point where we test our copy struct. Oh boy. Oh, this doesn't return anything. Well, no, it does. If returns either simulate turn or instantiate node. Oh, but if actions is nil. What to do? Well, we're mutating state, right? So we just return state. That's fine, right? Yeah. And that gives us back a new state. So now if we say question mark, what's going on there? Seems like we got some funny business. Where do we have unbalanced parentheses? Why it's an I? It's giving me an I, like, what? They're doing pretty printing. That is particularly alarming. Do we have? What's going on there? Let's redefine state just to be args out of range. Yeah, something's really weird. What is up with that? Are we mangling the struct when we do our copy sequence map shenanigans? I do wonder. That is making me a little curious. What is up with that? What to do, what to do. Oh, these things are always such fun. I guess we can just say Smaragdus copy struct st. And that gives us, oh, that gives us the args out of range. If we just print st, does same thing. Args out of range. What the fuck? What the fuck? Well, something weird is happening. I don't know if we are responsible for it, though. Right? I think Ion was maybe responsible for it. So Ion only prints this much of st. Actively, like, and then this doesn't have closed parentheses, and then this, yeah, oh, maybe this is it? Why is this so weird, dude? This is funky. Well. You just say that maybe does the trick for us. Yeah, that's closer to the right thing. That's frustrating though. I wonder what the deal is with that. Okay, so we have, as we'd expect, we have nil, we have the root node, and we have the state, which will just be instantiated from kind of nothing. Sure. And then what if we run a rollout from that? What if we want to roll out from, starting from, well, it's effectively Smaragdus copy struct st. Here's where we have something weird. Yeah. What the fuck? Something very questionable is happening. I'm getting a big old question mark over my head. It's just that this error is kind of inscrutable. Does that happen if we just run it from st? Well, no, rollout is going to do that regardless, I think. Yeah. Yeah. What if it didn't? What if it didn't, and then we tried that? Yeah, still broken. Still broken. Yeah, different in random ways based on the move being selected. If we toggle debug on error, yeah. It's inside resolve move. Huh. Oh, it's inside the struct lookup. Oh, we're fucking up the struct. But like that, we should just be like, if we're just running it on ST, that doesn't make any sense. Arg's out of range. We're encountering some real fuckery, I think. Something odd, I think. What could this be? Well, Lisp, we're just gonna Google. Lisp args out of range struct. Well, maybe like we would expect that to happen. Like if we say like aref poison powder 10, right? Yeah, that's the error, right? I think, right? Like also if we do ragdis rollout st, right? Like if we say aref spore 10, yeah, same error. So why is that aref happening, right? Like which field supposedly corresponds to index 10? Very curious. We're gonna solve this one, then we're gonna go sign off. We'll this has been a productive evening. Maybe we'll test some of this stuff offline because the debugging the debugging's fun. It's fun to do. It's kind of the meat and potatoes of the whole thing anyway, so can't really beat it. What is maybe we just need to reevaluate everything. Maybe that's what we need to do. Do we fuck something up with the moves? Somehow? Like, if we say spore, what is spore? Aref spore 0. Okay, that's like the tag. Sure, telling us what struct it is. That's the number. So 2. Sure. This will be 3, 4, 5, 6, 7, 8. This effect. Oh no, because there's empty fields. Types.el. Move. Right. 0, 1, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Should be effect. Sure. 9 is the effect. moves need to be reevaluated? Oh, maybe all the moves need to be reevaluated. Hey, Digby, what's up? Welcome back from work. It's kind of doing more debugging. We actually implemented the bulk of the kind of AI part today, the Monte Carlo tree search. So I haven't tested it much. We're kind of getting into that now. Hope you had a nice little day. Always good. Stay working. And welcome. All right, let's see. We're debugging some things that are kind of unrelated to the business logic of the whole shebang, and more related to like various vagaries of Lisp, which is not the most fun, but it'll do. Does that fix it? Yeah, we had to reevaluate these things. Okay, we're gonna change all of these to setfs because defvar is a dangerous little guy, and I don't think that I like him very much in the context of defining temporary variables for testing. Okay, val buffer. This should reload everything. Yeah. Okay, now if we run a rollout, okay, we get an actual result. We should always get unknown because there's no way to actually win these battles. Let's actually make it so someone can win. Let's make it so everybody can win. Val buffer. Team 2 wins. Team 2 wins. Team 2 wins. Are we not doing the copy? Let's make them have actually identical. Do they have identical teams? Oh yeah, well they don't right now, but they should. Just with different starting creatures. Eval this buffer again. Unknown. Team 2. Team 2. Are we copying the thing correctly? I mean, team 1 active HP ST. Tried getting an AI like ChatGPT to make a section you've already done and compared the code. I have not. Yeah, that might be interesting. I have not used any kind of LLM based AI for any kind of coding at all. Might be interesting to do. Assume it has a reasonable corpus of Emacs Lisp, so might be interesting. Yeah, it might be fun. It might be actually a whole lot of fun to do on stream. We could build a I mean, I know there's a new GPT-3 API from OpenAI that's like super cheap, right? It's like 10x cheaper than the previous API they had. So we could build like an editor extension. I mean, this whole thing is already a big editor extension, right? We could build like some kind of integration with that. Maybe that would be a fun side stream. I might do that. Also, I think Facebook's model just got leaked, so you can actually, like, if you have 65, like, if you have like tons of VRAM, you can run something reasonably close to ChatGPT locally, which could be cool. I don't have tons of VRAM, but could get it maybe. Okay. Well, this is clearly not copying correctly. Yeah, I mean, they had this process. It was like relatively more open than OpenAI's, I think, in the sense that like it wasn't totally closed off, but you had to like fill out a survey to get it, and like they were giving it to like anyone, like people with like .edu emails and like a reasonable use case and stuff. But it wasn't totally open, and there's like licensing conditions on it. Someone just like uploaded a torrent, which I assume they must have expected, right? Like they weren't exactly making it incredibly difficult to get at the thing, and of course it's going to spread around. So things like I saw on Hacker News the other day, someone had left someone had publicized the torrent by adding a pull request with the magnet leak to like the official repo for the model, which was very funny, like saying like you can save bandwidth by just downloading it here instead of Yeah, very, very, very droll. Okay, so this is fine now. Okay, where's the back over to the actual AI file? Where's our rollout? Rollout. Okay, we should be copying structs. Yeah. That's sort of what I'm like. How can you expect it to not get stolen? Okay, so something is going wrong with our copies. That's fine. We expect copy struct at the beginning of our rollout to be a deep copy, but clearly it is not a deep copy. That is interesting. Well, we wrote copy struct ourselves, and we weren't super confident about it, so maybe we can think a little harder. This is something I do not miss from imperative languages, worrying about deep and shallow copies and all this. Like, everything should just be immutable. It shouldn't matter whether you pass by reference or pass by value. It should be the same, like, that should be a performance optimization to be handled by the compiler. It's all just immutable data. So we have a very simple logic here. What could be going wrong? Maybe it's not a sequence P? Is ST a sequence P? well, that certainly does the trick. But can we copy sequence ST? Yeah, we can. Well, is it an array? No. Well, sure, it's going to give us that. Blah. If I say map it st, does that work? That's not helpful either. How do we map? If I say copy sequence st, yeah, that does a thing. What does copy sequence look like? A copy of a list, vector, string, char table, or record. Is it a record? Oh yeah, it is. Can we do things on records? How fun this all is. Oh. elisp map over record. It's not going to use that term. Oh, we have sequence functions. Can we just say they're just a nice map? Like, I want to be sure. Seek map. If I say, okay, seek map lambda it st, it doesn't return the right thing at all. Turning, oh boy. Seek map. Record. Copy sequence takes either a sequence or a record. That's the only mention of record in this page. I don't know why I thought we could treat a record like a sequence. Is there an array map? Oy. Oy, oy, oy. Oh, we have functions that operate on arrays. Well, those are very limited. I guess we can do this. We can copy the sequence and do a bunch of mutable. Oh my gosh. How horrid. How positively horrid. Over struct. I'm gonna say deep copy struct. This is going to give us some common Lisp results. Oh, we're gonna have to do something kind of nasty probably then. That's fine. Well, what we do then, I think, is we just say let new we need to be careful here, right? Because there's explicitly things that we don't want to copy, right? We don't want a full deep copy. We just want a copy like to an appropriate level of depth, right? Because some things at the bottom, right, like the species structs and the move structs, we don't need to copy, right? They're immutable. How frustrating. You know what? Maybe we'll put a pin in it. I think it's getting late and I'm getting tired and grumpy. So I think we will put a big to-do. Make this actually copy the appropriate things. Right now it does not work at all. We'll figure that out. Maybe it comes down to writing a custom copier for every struct in our, or generating a custom copier for every struct in our whole shebang. That's fine if so. It'll just be a little bit of boilerplate. I think it's okay. For now, we're gonna call it. Keep it a little shorter. We'll be back again next week, probably Friday. Friday is the usual day. Maybe more than Friday, but I'm quite busy right now, so unfortunately limiting it to just once a week is the reality. Yeah. All right. Do we have anybody to raid? Do we have any people watching? Do we have anyone to raid? The eternal question. Who's up? Who's up at this hour? Not too many. Too many of the homies. Let's see what our raid quotient looks like. Corpse is around. Maybe a raid corpse. Playing some RPG action, some more laid back, experimental VTubing content. Let's see. What does this look like? What are we looking like? 4 viewers, 7 viewers. There we go. 8 viewers, 9 viewers. Let's fire it off. Thanks, guys. It's a lot of fun. We'll be back soon. Do more of this nonsense.